Hey guys, thanks for checking out this video on sections 11.5 and 11.6. I know that knowing that you're all finished with grades and that this is really just enrichment material, it's probably a tough thing to motivate yourself to watch these, but I appreciate it very much, and I think it'll do you some good in the long run. So to begin with, in section 5, we're going to talk about some counting techniques. And there's a couple different types of counting techniques in particular that we care about. And the first is called a permutation. And the idea here is that you have some, maybe relatively large group of items, and you want to select only some of those items. And you want to know how many different ways you could do that. And with permutations in particular, the order in which you select those items matters. So we're going to look at a second possibility here where maybe the order doesn't matter in a moment, but you need to try to remember that a permutation is a case in which the order that the items are selected in matters for some reason, okay? So the formula that we use to calculate a permutation is this. Remember, we talked about factorials last section, I think, or the section before, maybe one of the first sections on sequences. They're starting to kind of blur together on me, but we've talked about factorials here recently, and here they are showing up in this formula for the permutation. So n items taken r at a time works out to be n factorial divided by n minus r factorial. So here's an example to help us see how this works. Suppose we want to elect class officers. So we'll have a president, a vice president, a secretary, and a treasurer, and we want to pick those 4 people out of a class of 20 students. So in this case, the n would be 20, the number of students we have to choose from, and r would be 4, the number of students that we're actually choosing. So we set up our permutation this way, and then obviously 20 minus 4 is 16, so this simplifies to 20 factorial over 16 factorial. The difficulty here with these factorials is that they're really large. Okay, 20 factorial is something, I forget, 1 point something times 10 to the 18th power. Okay, so it's in the billions. And it's only, 20 factorial. We're not even dealing with 50 factorial or 100 factorial. This is still a relatively small number. So we need to try to get this down into something that's a little more manageable. And so what we want to observe is that 20 factorial could be written this way, as 16 factorial times 17, 18, 19, and 20. Okay? That means that the 16 factorial in the top of the fraction can be simplified with the 16 factorial in the bottom of the fraction, and it would just leave us with 20 times 19 times 18 times 17, which is not too easy to do by hand, but it's also not completely unmanageable. So if you needed to do it by hand, you could get there, right? 116,280 is our final answer. Obviously, you don't have any homework on this. I'm not going to take away your calculators. So the calculator is available to you most of the time when you're doing these, but it's nice to know some ways to simplify these big numbers and get them into something more manageable. So this number is pretty significantly large, considering we started out with 20 students. We only chose 4 people. There are 116,000 different ways to do that. So in some cases, though, there may be some objects that are indistinguishable from other objects. These are examples where maybe you've got 5 blue marbles and 4 red marbles and 6 yellow marbles. Did I say yellow twice? Anyway, you've got some objects that you can't really tell apart from each other, right? You can't tell 2 blue marbles apart. You can't tell 2 yellow marbles apart. They look like the same thing. And so this brings up the idea of something called a distinguishable permutation. So in order to account for the fact that you could pull or that you could arrange 2 different items differently, but it would seem to be the same, like there's no way to tell, then we need to change our formula. And the way we do it is we take n factorial, which is our total number of objects. So this would be like the total number of marbles in the bag, divided by n sub 1 factorial, that would be like the number of red marbles, n sub 2 factorial, that would be the number of blue marbles, etc., etc. Okay, so here's just kind of a quick and easy example that we can look at that doesn't use marbles. It actually uses letters of the alphabet. So say you take a word like Tennessee, and you want to know how many different ways could we rearrange the letters in the word Tennessee. Okay, not necessarily to make new words, just to arrange the letters differently. So first thing we need to know is how many letters are there in the word Tennessee? 1, 2, 3, 4, 5, 6, 7, 8, 9, looks like. So 9 factorial goes in the top. And then for the bottom, we look at each letter individually and just identify how many times does that occur. So the T only occurs once. That's why we have the 1 factorial first. And then E shows up 4 times, so that's 4 factorial. Then N and S both occur twice, so they both get a 2 factorial. So now, to simplify this one, we're going to do something similar. The 4 factorial in the bottom is the biggest factorial that we have. So we're going to simplify that with some of the pieces in the top. So the 4 factorial, and the 1 factorial is just 1, so it goes away. But the 4 factorial simplifies with 4 times 3 times 2 times 1 out of the top, which just leaves us with 9 times 8 times 7 times 6 times 5 divided by 2 factorial. Well, the value of 2 factorial is just 2. So I'm just going to take the 2's there in the bottom, and I'm going to simplify them with the 2 even numbers that are in the top. So that's going to give me 9 times 4 times 7 times 3 times 5. Okay, so 8 divided by 2 is 4, and 6 divided by 2 is 3. So giving us a final answer of 3,780 different ways you could rearrange the letters in the word Tennessee in such a way that you could tell those ways apart. Okay, so like for example, if I just interchanged the 2 N's, we wouldn't be able to tell that I had done that. So that wouldn't count in this 3,780. Okay, so this is the number of different ways that we could arrange the letters. That's a distinguishable permutation. Our third major topic here is combinations. A combination is similar to a permutation in that we have a bunch of objects and we only want to select some of them, but the big difference here is the order in which we select those items does not matter anymore. Okay, so the example here would be something like, say you just want to form a committee as opposed to having class offices like president, vice president. Everybody's equal. They're just, in a group together. You're just trying to see how many different ways could I select this group. So that's kind of the idea behind a combination. And the formula for a combination changes just slightly. Notice that it's, instead of being n factorial over n minus r factorial, now there's an additional piece, n factorial over r factorial, n minus r factorial. And I want to point out here on this notation, this center notation with the big parentheses and the n stacked over top of the r, that is the n choose r notation. It's the way we read that. So you have n items and you're going to choose r of them. That's just a kind of because combinations are actually more common in math than permutations, they have kind of their own special notation, and we have a way that we read them. We just say n choose r. So if n was 20 and r was 4, we'd say 20 choose 4. Okay, so just want to make you aware of that notation and the kind of the way you verbalize it. So for the example, this is just what I mentioned a moment ago. Same kind of scenario. We want a committee of 4 people, but no titles. So the order in which people are selected don't make a difference. Okay, you get a senior, a junior, a sophomore, and a freshman on there. It doesn't matter what order you select them. They're just 4 people on a committee, and it's a-okay. So here we have the formula. Okay, 20 is again our n. So 20 factorial over 4 factorial, 20 minus 4 factorial. Now 20 minus 4 is still 16, right? So this is 20 factorial over 4 factorial times 16 factorial. So I'm going to simplify the 16 factorials just like I did last time, okay, in exactly the same way. With 4 factorial, the value of 4 factorial is 24, right? It's 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24. So I can still simplify this a little bit, even though 24 itself doesn't really divide any of these numbers. I can take the individual pieces and simplify. So like, for example, 20 is divisible by 4, right? So I can do 20 divided by 4 and get 5, and that'll work. And that leaves me with 3 times 2 times 1. So 3 times 2 is 6. 18 is divisible by 6, so that would leave me with a 3 in the top. So that's what I did. So 20 divided by 4 gives me 5. 18 divided by 6 gives me 3. And that leaves me with 5 times 19 times 3 times 17, which is 4,845. So notice something important here. There is a big difference between the value of the combination 20 choose 4 and the permutation 20 choose 4. I probably shouldn't say it like that. 20 P4. We'll just say it like that. The value of the permutation was 116,000 something, and this one's only 4,845. So when order matters, that tremendously increases the number of possibilities. So so just kind of keep that in mind. Combinations are typically much smaller than permutations. Okay, that wraps up our conversation on section 11.5. The reason this section is stuck in here is because in section 11.6 we need combinations in order to do the binomial theorem. So coming up next will be section 11.6 on the binomial theorem.